All right, let's jump right in. Today we're tackling processors, those tiny chips that are in, well,
They
everything.
really are everywhere, aren't they?
And the thing that gets me is how the same code can run on my phone, my laptop, even my smart fridge,
It's one of those things most people never think about, but it's pretty amazing when you stop and consider it.
for sure. And we're going to get to the bottom of how that all works. We're going to decode stuff like CISC, RISC, by64, even dotnet.
Oh yeah, we're going deep. All from this pretty technical document about how computers translate code. It's a bit dense, but we'll keep things interesting.
We've got to start with the basics, though. Processors or CPUs. What are they exactly? Why should we care?
Okay, so think of a CPU as the brain of your device. It's constantly processing instructions, like super fast, to keep everything running smoothly.
Okay, that makes sense. But this document's talking about all these different types of processors, CISC, RISC. It's a lot.
Yeah, there are quite a few, but don't worry, we'll break it down.
Please do.
All right, so CISC and RISC, they're like two different philosophies of processor design. Think of CISC, complex instruction set computing, like a multi-tool.
Okay, I can picture that.
It's got a ton of different instructions to handle all sorts of tasks, like Intel and AMD processors, the ones you find in most desktops and laptops. They're based on CISC.
So that's why those devices can do so much. They've got the CISC power.
Exactly. Now, RISC, that stands for Reduced Instruction Set Computing. It's a little more minimalist.
Aminoless, huh?
It focuses on a smaller set of instructions, but they're simpler, and often that means they can execute faster.
So like less is more.
In a way, yeah. Your smartphone, for example, uses an ARM processor, which is based on RISC.
Really? So my phone is running on a minimalist processor.
It might seem counterintuitive, but it works. RISC processors are really efficient, which is perfect for mobile devices where battery life is super important.
That makes sense.
Yeah.
Now, the document also mentions GPUs, which are the things that make games look so realistic.
Absolutely. GPUs are all about parallel processing. They can handle tons of calculations at the same time, which makes them perfect for graphics.
Okay. Yeah, I get that. But they're used for more than just games now, right?
Oh, yeah, way more. AI, machine learning, anything that needs serious processing power.
It seems like those fields are just exploding right now.
Definitely. Now, there are also SOSIs, these things that make our phones basically tiny supercomputers. How do they pack so much power into such a small space? It's pretty remarkable, isn't it? It's called system-on-a-chip technology. Basically, they put the CPU, the GPU, memory, everything onto a single chip.
That's crazy. It's like they shrunk down a whole computer.
Yeah, and that's what makes it possible to have such powerful smartphones that still fit in your pocket.
I've got to ask about this one. Quantum processors. The source mentions qubits instead of bits, and honestly, it sounds like something out of Star Trek.
It does sound futuristic, doesn't it? But quantum processors are a real thing. They use quantum mechanics to do calculations in ways that classical computers just can't.
Wow, that's next-level stuff.
It's still early days, but the potential is huge, especially for things like cryptography or drug discovery. Now, before we get too lost in the quantum realm, let's go back to something you mentioned earlier, by64.
Oh, right. The source mentioned that in relation to CISC. Is it a totally different type of processor?
Not quite. It's a common misconception. By64 is a 64-bit version of the by86 architecture, which is actually under the CISC umbrella.
Okay, so it's like a newer version of CISC.
Basically. It lets processors access more memory and process information more efficiently. Most computers today run on by64 processors.
So it's like CISC leveled up.
You could say that. Now let's talk about assembly language.
Oh, right. That's like the language processors actually understand, isn't it?
Exactly. It's a low-level programming language that's super close to the actual machine code that processors execute.
So it's the secret code that makes all the hardware work.
Yeah, you could think of it that way. Now the question is, does assembly language change with the type of processor?
I'm guessing the answer is yes, but I'm not sure why.
You're right. And the reason is that assembly language is directly tied to something called the instruction set architecture, or ISA, of a processor.
The ISA. What's that?
It's basically the processor's vocabulary, the set of instructions it can understand. Different processors have different ISAs.
Ah, that makes sense. Okay, so now we're getting to the part that blows my mind.
Mm-hmm.
Code portability. How can code written in, say, C#, which is designed for humans to read,
Right.
How can that run on machines with totally different processors? It seems impossible.
It's definitely one of the most fascinating aspects of computer science. But to understand it, we need to dive into the world of layers of abstraction.
Welcome back. Before the break, we were talking about assembly language and the idea that every processor has its own unique way of speaking, like its own dialect.
Right, exactly. And it's pretty mind-blowing how code written in a human-readable language like C# can actually run on all these different processors with their different dialects.
Totally. So how does that work? How do we bridge that gap?
That's where things get really clever. It's all about these layers of abstraction that programmers have built over the years.
Layers of abstraction. Okay, you're going to have to break that down for me.
Sure. So high-level programming languages like C#, Java, or Python, they're designed to hide all those nitty-gritty details of the hardware. They let programmers focus on the logic of the program without having to worry about the specifics of the processor it's running on.
Okay, I'm starting to see how that helps with portability. But how do we actually translate this human-readable code into something the machine can understand?
Good question. That's where compilers and interpreters come in. You've probably heard of them, but they can be kind of confusing.
Definitely. I always get those two mixed up.
Okay, so imagine you have a book written in a foreign language that you want to read. A compiler would be like translating the entire book into your native language all at once so you can just sit down and read it.
Okay, so with a compiler, you've got the whole translation up front.
Exactly. C and C++ are examples of compiled languages. Now, an interpreter is more like having a friend who reads you the book aloud and translates it for you sentence by sentence as you go.
So it's like real-time translation.
Exactly. Python is a good example of an interpreted language.
So compiled languages, they get the whole translation up front, which seems like it would make them faster. But with interpreted languages, you get more flexibility because the translation happens on the fly, right?
You got it. There are definitely trade-offs. Compiled languages tend to be faster because that upfront translation makes them more efficient at runtime. Interpreted languages, on the other hand, are often easier to work with, especially for beginners, because you can test your code and make changes more quickly.
Makes sense.
Mm.
So there's no one best approach then?
Nope. It really depends on what you're trying to do. But since we're talking about code portability, and our source material focuses on C#, let's zoom in on how that works in the .NET world.
Yeah, let's get specific.
All right, so remember how we talked about the CLR, the Common Language Runtime, in the previous part?
Vaguely. Refresh my memory.
Well, it plays a big role in .NET's portability. When you write code in C#, it doesn't get compiled directly into the machine code for a specific processor. Instead, it gets compiled into something called intermediate language, or IL for short.
IL, what's that all about?
Think of IL as a kind of universal language for the .NET world. It acts like a bridge between your C# code and the specific processor it needs to run on.
Okay, so it's like a middleman that helps with the translation.
Exactly. Then the CLR comes in. It's like a universal interpreter for .NET. It uses something called a just-in-time, or JIT, compiler to translate the IL into the native code for whatever device it's running on.
Okay, and all this is happening behind the scenes while the program is running.
That's right. And that's how the same C# code can run on a Windows PC, a Mac, or even a Linux server, even though they might have completely different processors. The CLR takes care of all the translation.
That's pretty slick. It really is like magic. The source mentions something called .NET Native AOT compilation, though. What's that all about?
Yes. AOT stands for ahead of time. It's a different approach to compilation that offers some interesting benefits. Remember how we talked about compilers translating an entire book up front?
Yeah, like getting the whole translation done before you start reading.
Well, that's essentially what .NET Native AOT does. Instead of using a JIT compiler at runtime, it compiles the code directly into native machine code during the build process.
So it's like the translation is already done before the program even starts running.
Exactly. And that can make things a lot faster, especially for applications that need to start up quickly.
Sounds great. But there must be some downsides, right? Nothing's ever perfect.
True, there are always trade-offs. One of the main drawbacks is that it can be a bit harder to debug AOT compiled code.
Harder to debug. Why is that?
Because the code is already pre-compiled, there's less information available at runtime for the debugger to work with. It's like trying to figure out how a machine works after it's already been put together.
Okay. Any other limitations?
Some of the dynamic features of .NET, like reflection, might not work as well with AOT compilation. But it's a powerful technique, especially for situations where performance is really important, like with mobile apps or cloud services, where you need things to be as fast and efficient as possible.
So it's not a one-size-fits-all solution, but it's got its place. This whole discussion about compilers and interpreters and .NET makes me wonder about other languages. Like, what about Python? How does it handle portability since it's an interpreted language?
That's a great question. It's a bit different with interpreted languages. Remember how we talked about the interpreter being like a friend who translates the book as you read it?
Yeah, that real-time translation thing.
Well, in the case of Python, there's a different interpreter for each operating system and processor combination.
So there's a Python interpreter for Windows, one for Mac OS, one for Linux, and so on.
Exactly. But the cool thing is that the Python code itself can stay the same. You don't have to rewrite it for different platforms.
That sounds much simpler than having to deal with all these different compilers.
It can be, yes. Achieving portability is often easier with interpreted languages. But there is a trade-off.
Another trade-off.
Because the interpreter is doing all that translation in real time, it can make things slower compared to compiled languages where the translation's already done.
So it's that speed versus flexibility thing again. Faster execution with compiled languages, but easier portability with interpreted languages.
Right. It's fascinating how different languages have found different solutions to this challenge. And it shows how important portability is in the world of software development.
This deep dive has been incredible. I had no idea how much goes on behind the scenes just to run a simple program.
It really is amazing, isn't it? And the story doesn't end there. We're only just scratching the surface of what's possible with code portability.
Speaking of what's possible, you hinted at some really exciting developments in the future of code portability before the break. I'm dying to hear more about that. Welcome back. We've covered so much ground already, different types of processors, how code gets translated. But there's still one big question. What's next? What's the future of code portability?
Well, the future of code portability is kind of tied to some pretty big trends in tech, like cloud-native development and edge computing. These are really changing how we build and deploy software, and they bring some new challenges, but also a lot of really exciting possibilities.
Okay, so let's start with cloud native. What does it even mean for code to be cloud native, and where does portability fit in?
Imagine building an application that isn't tied to any specific server or physical location. It's designed to run across a whole network of servers, scaling up or down as needed. That's the idea behind cloud-native development.
So it's like flexible and adaptable.
Exactly. And in a cloud-native world, portability becomes even more important. We're not just talking about running the same code on different processors anymore. Now it's about running it on different cloud providers, each with their own infrastructure and services.
So it's a whole other level of complexity. How do developers even make sure their code can handle all that?
It's a challenge, for sure, but there are new tools and frameworks popping up all the time to help. Containers, for example, they're changing the game when it comes to packaging and deploying applications.
Containers, like those big metal boxes on ships.
Haha, similar concept, but much smaller. A software container is basically a self-contained unit that holds everything an application needs to run. The code, libraries, dependencies, all bundled together.
So it's like a portable little environment for your application. It can just move between different cloud environments without any problems.
Exactly. Containers abstract away all the complexities of the underlying infrastructure, making applications much more portable and flexible.
Okay, I'm starting to get it. Now, what about edge computing? You mentioned that earlier. How does that fit into the future of code portability?
Well, think about all the devices we use every day. Smartphones, smartwatches, even smart appliances. All those devices are generating tons of data. With edge computing, the idea is to process some of that data locally, right on the device itself, instead of sending it all the way to the cloud.
Oh, that makes sense.
Yeah.
So it's like instead of relying on a central brain in the cloud, edge devices have a little bit of their own intelligence.
Exactly. Edge computing is great for reducing latency, improving response times, and even for privacy, because you're keeping sensitive data on the device itself. But it also brings up new challenges for portability.
How so?
Well, edge devices often have limited processing power and memory compared to those big cloud servers.
So the code needs to be really lightweight and efficient to run on those devices.
Right. And that means we need programming languages and frameworks that are specifically optimized for edge computing that can run smoothly on everything from tiny sensors to powerful smartphones.
This is all really fascinating. It seems like technology just keeps getting more complex and interconnected.
It definitely does. And this idea of code portability is at the heart of it all. As our world becomes more and more reliant on all these different devices, being able to write code once and have it run everywhere is only going to become more important.
So after this amazing deep dive, what's the one key takeaway our listeners should remember?
I think the biggest takeaway is to really appreciate the power of abstraction. From high-level programming languages to virtual machines and containers, all these layers of abstraction are what make code portable and adaptable. They free us up to focus on the logic of our programs without having to worry about the nitty-gritty details of the hardware or the platform.
It's like having a whole team of expert translators working behind the scenes to make sure our code can speak the language of any device anywhere in the world.
Exactly. And as technology keeps evolving, we're going to see even more layers of abstraction emerge, bridging the gaps between different computing environments and allowing us to build software that's truly portable and future-proof.
Well, this has been an incredible journey. Thanks for joining us on this deep dive into the world of processors and code portability. We hope you've learned something new and that you're as excited about the future of technology as we are.
It's been my pleasure. Keep exploring, stay curious, and remember, the future of technology is built on the foundation of code that can break down boundaries and empower us all.